Okay, back at the VCAA 2021 physics exam, back in section B, and question 5 here. So figure 5 shows a stationary electron. So stationary electron in a uniform magnetic field between two parallel plates. Plates are separated by a distance of 6 by 10 to the minus 3, and they're connected to a 200 volt power supply and a switch. Initially, the plates are uncharged. Assume that the gravitational effects are negligible. All right. It says for part, so here's our situation. So we've got an electron sitting there inside this magnetic field. At the moment, this switch is open, so there's no electric field between the plates. All right, so explain why magnetic force does not exert a force on the electron. Well, if the electron is stationary, that means that its velocity is equal to 0, and the magnetic force formula for that is QVB, and so V is equal to 0, therefore our magnetic force is also equal to 0. All right, so 2 marks on that. So you had to identify this, that it's stationary, so no velocity. All right, then we go into part B. And in part B, when I get to it, on the next page, here it is. Determine, the switch is now closed. Determine the magnitude and direction of any electric force now acting. All right. So the electric force formula, electric force, the force electric is the charge times by the field. Now, the field, of course, is the voltage on the distance, and we know that the thing's an electron, so its charge is 1.6 by 10 to the minus 19. And the voltage, when we were told that, the voltage was 200, and the distance between the plates was 6 by 10 to the minus 3. And we get our calculator and we work that out, and we get 5.33 by 10 to the minus 15 for our electric force. All right, and determine the magnitude. Done that, so I'm going to put it in the box. 5.33 by 10 to the minus 15. Make sure you use the right notation, the time power of 10 notation, not necessarily what your calculator tells you. And it says your direction. So your direction, and we have a look, go back here. So the direction of the force on the electron. Now, when this is closed, this top plate here is connected to the negative, so that becomes negative, and that other plate becomes positive, so the electron is going to go down the page. It's going to be attracted towards the positive plate, so down page. All right, so the last part of this question has to do with Ravi and Mia discuss what they think will happen regarding the size and the direction of the magnetic force on the electron after the switch is closed. All right, so what this relies on is thinking about the before and the after. Now, before the switch was closed, the forces were balanced, the electron was stationary. When you do close the switch, you now got this electric force that we've calculated up in part B. So the forces are no longer in balance. So if the forces are no longer in balance, the thing is going to start moving. So switch closed. So before I get to that, so when switch closed, forces no longer balance. And if the force is no longer balanced, that means we have acceleration. All right. Okay, so Ravi says that there will be a magnetic force of constant magnitude continually changing direction. Mia says there will be constant increasing magnetic force, but always acting in the same direction. All right, so our magnetic force is QVB. Now, we've got an acceleration, so we've got a velocity that will be changing. All right, so because we now have acceleration, because the forces don't balance, so some of the forces not equal to zero, this means, oops, it's not equal to zero, therefore we have acceleration, which means that V is changing. All right, so if our velocity is then changing, our velocity is changing, so then what that means then is the magnetic force is also changing. All right, so what have we got going here? So Ravi says there will be magnetic force of constant magnitude. Well, that's incorrect. Continually changing direction. Well, yes, that will change direction as the direction of our velocity changes. So Ravi is correct about the direction. Incorrect about the size. All right, and Mia says that the constantly increasing magnetic force. Well, that's correct because the velocity will be increasing. So velocity was zero, it's going to increase if it accelerates. So that's true, but always acting in the same direction. Well, no, there's a magnetic force in there as well, so that's going to cause a deflection. Sorry, magnetic field, I should say. So that's going to cause a deflection. So Mia is correct about the size of force. And incorrect about the direction. All right. All right, so it's more likely it's going to move in a circular kind of path. So that would mean that the direction of the force and the direction of the velocity would be continually changing. All right, so that's my take on part C. I would suggest you make sure you look at the VCAA report and also your teacher, speak to your teacher and get your teacher's take on that one. All right, so there's 4 marks here. So I think you need to identify what happens when the switch closed. The force is no longer balanced, therefore we've got an acceleration there. So if we've got an acceleration, we've got a change in velocity. All right, I should put a therefore there really, therefore, which means that the magnetic force is also changing. And then Ravi and Mia both have one aspect correct and another aspect incorrect. All right, let's move on to the next one. Question 6. Question 6. Figure shows an AC generator. Mechanical energy source rotates the loop in the direction shown. 50 revolutions per second. And we've got a RMS voltage of 4.2 volts. Magnetic field is constant and uniform in that particular direction. All right, so if we've then got a frequency of 50, what that means is that our period would be 1 on 50, which would be 0.2 of a second. All right, so we might need to know what that time is for the full rotation. All right. Sketch the output EMF between. All right, so I do need to know that time period. So I need to know that time period. I'm also going to need to know the peak voltage. So VRMS is 4.25, and so V peak would be root 2 times 4.25. And so when you do that in your calculator, 6.01 volts. All right, so we need to sketch this. So you've got to put some labels on. In the vertical axis there, you'll notice they've already got 10s marked, and there is in fact 10 things there. So 1, 2, 3, 4, 5, 6 is where 6 is. Of course, we need to go down -6. Time periods. All right. So show at least 2. So we need to show at least 2 complete revolutions, include the maximum voltage on the vertical axis and a time scale on the horizontal axis. All right. And so what am I going to do here? I'm just checking my notes. My notes, I've gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's 0.01, 02, I should say. And then 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 0.04, because we want 2 cycles, and remember 1 period is 0.2. So if I start here, I'm going to go up to its maximum there, on its way down to here, and down to its minimum there. There's 1 cycle, and then repeat for the second cycle. There we go. And so then draw it in as neatly as you possibly can, better than that, hopefully. All right. Okay, and I know that the maximum voltage is 6.01. But given that scale, yeah, it's going to be very difficult to do that. And don't forget to label your axes, because it actually asks for that. So some of those 4 marks is for labelling the axes with these particular numbers. All right, and you can put 0.01 there and 0.03 there if you liked. All right, so part B says, describe the function of the slip rings. Simply put, slip rings, all they do, their purpose is to maintain electrical contact between the loop and the outside circuit. Right, that is their sole purpose, is to do that. Now, if you didn't have slip rings and just connected it up with wires, those wires would very quickly get twisted up and the thing would stop rotating. All right, but what do? They maintain the electrical contact. All right, how could the AC generator in figure 6 be changed to a DC generator? All right, now, got to be very specific with this particular thing, and the thing that you would need is to replace the slip rings with now here's where you need to be specific, a split ring commutator. All right, because in a generator, the whole purpose of a split ring commutator is to change AC to DC. And so you've got to be very specific with that particular wording there. All right, then it says sketch the output of the EMF at least 2 revolutions for the DC. All right, so effectively what happens is this bit that's down here now gets flipped up into there. All right, so let's have a look. And this time we don't have to put a scale, it doesn't on the vertical axis. All right, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, that's my 0.02. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, that 6 that I've counted across there is nominal. I just going to make sure it's an even number. All right, so we start here. We go up, 2, 3, 4, 5, up to there. We come back down here. Now, instead of coming down here, we're going back up again. So we come up to here, up to here, up to here, and there. All right, so now our thing looks like, whoa, let's see if you can draw it a bit better than me. Like so. All right, so that's what we are looking for in that, for that particular graph. All right. Now, what I didn't explain is why I've gone up first. And now I should have explained what I did with that. And what I should have done is we've got to refer to, of course, the EMF. And so EMF is negative and changing flux with time. So we've got this negative here. So the EMF, it's the negative change in flux. All right, and so at the moment where we've got this in this orientation, our flux is a maximum. So it's at a maximum, and as we rotate, the flux is going to decrease. And it's going to go through the other side of the thing, of the coil, and so on. So it's going to go like that. So if we've got negative change in flux for our EMF, then if the flux is decreasing, then the EMF has got to be the opposite to that, which means increasing. Flux is decreasing from here to here, so it's got to increase from there to there. All right, and so we end up getting something that goes like that. It's also related to the gradient of here, 0, that's why we start at 0. Maximum, the negative gradient, but don't forget there's this negative here. So if it's a negative gradient, the opposite to the negative is positive. All right, so that's another way of looking at it. Okay, so sorry, I should have actually gone through that when I first started drawing the graphs. So that's why I've made my graphs go the way I have. All right, next question, question 7. Is the next one. Let's go over here. Question 7. A generator of an electrical power plant delivers 500 megawatts to external transmission lines when operating at 25 kilovolts. The generator's voltage is stepped up to 500 kilovolts transmission and then stepped down 100 kilometres away. The overhead transmission lines have a total resistance of 30 ohms, sorry. Assume that all transformers are ideal. So if the transformers are ideal, then there's no power loss in the transformers. The only power loss that we're interested in is the transmission lines. All right. And the power loss in the transmission lines is, of course, I squared R. Is the main one. All right, so explain why the voltage is stepped up for transmission along the overhead power lines. Transmission lines. All right, this is exactly what I've talked to here. So voltage stepped up. What does that mean? Current reduces. And so what that is, we reduce power loss due to I squared R. All right. Now here in this particular one, we're stepping it up from 25 kilovolts to 500 kilovolts. So that's a factor of 20. So voltage up by a factor 20, which means that current is reduced by factor 20. Which means that the power loss is down by factor 20 squared, which is 400. All right, so that's a fairly detailed here for 2 marks, but essentially you step it up because then you can reduce your current through the transmission lines, which reduces your power loss. All right, so calculate the overhead transmission current in the transmission lines. All right, so for this we've got ideal transformers, so power in equals power out. All right, so the power in that we're told that we're getting in, here we are here, 500 megawatts. So 500 megawatts, 500 mega is 10 to the 6 equals power out. All right, so voltage is stepped up to 500 kilovolts. So power out, I'm using VI, so P equals VI. So the power out is 500 kilovolts by 10 to the 3 times the current. And when you work out that current is 1000 amps. Now when we look in our, excuse me, in our box here, it says kilo KA, so that's 1000 is a kilo, so it's 1 KA, so 1.0 KA. All right, determine the maximum power available for domestic use, showing all your working. All right, so my power, so it's 3 marks, so there's a bit to show here. So yeah, there's actually 2 steps to the process and you need to show both steps. So the power loss in the wires is I squared R, which is 1000 squared times 30, which is 30 by 10 to the 6 watts. So the power available at domestic use is what we started with, what we put in, and remember we put in 500 by 10 to the 6 into it, 500 by 10 to the 6, and then we lose 30 by 10 to the 6. And so we've got 470 by 10 to the 6 watts available to us. So I want it in megawatts, so that's of course just 470. All right, there's question 7. All right, I think I'll do one more question for this particular video.